All right, so I got here the homework from most everybody. I think there's a few people that were going to turn it in late. But I should have that to you guys by by Thursday. I'm not having it to you tomorrow. And that's hopefully by Thursday. I've got somehow a bunch of meetings that just need to pop up. So I don't know how much grading time I'm going to get, but I'll try to get this guys to you by Thursday. If not, we're going to be busy with the questions from today, I'm sure, on Thursday. So I don't think that we're going to have any lack of things to discuss on Thursday. And also I want to give you a heads up. I was invited to give a talk in San Antonio on December 1st. So what I think we're going to do is actually usually I don't have a lecture the week of Thanksgiving. So I think what we're going to do is we're going to actually have a class on that week of Thanksgiving for the lecture, but we're not going to have a recitation that week because, it's Thanksgiving. And for some reason, you guys never want to show up on Thanksgiving for class. Nobody ever brings the turkey. Nobody wants to show up. It just happens every year. So we'll probably do the recitation for that one after Thanksgiving. And I think that might actually be the review for the final exam that we might do then. I'll just see when the schedule falls. So, but either way, it's the same total number of lectures for the week. Is there a question?
Oh, yes. There's a problem with the homework. I was actually turned it in, but I thought I was booked online.
Yeah.
I was trying to see if I could send it, if I could rework that one out.
You could do it, as long as it's before Thursday. Because Thursday's my drop dead date, because if I'm going to go over this stuff in class, I need to have it by then. So I can still entertain it before then. Before Thursday. Don't try to abuse that because I don't have that much time. All right, and so like I said, I can't make, this is probably the worst week for me to make promises on grading, but I'll see what I can do. And then also I did post the next homework that you guys are going to have. It is on Blackboard. And what I'm assigning, this is problem set number 5. And you're going to have, actually let me write it on here. Problem set number 5. And the good news is there's only 5 problems. The bad news is that if you're paying attention, 5 problems in this class is not necessarily 5 minutes of work. So from Matthews and Walker, you have 3 problems: 9-3, 9-7, and 9-10. These are all problems over eigenvalues. And then Arfken and Weber, eigenvalues and Green's functions, I should say. Arfken and Weber, there's 9.25 and there's 9.45, which I believe are both on differential equations. And these are due in November 10th. That's 2 weeks from today. So this is the second to last homework. And so, like I said, I expect that by now everything's rolling along. And even though there's only 5 problems here, I wouldn't wait till the last minute. I would say, start on the ones you can start on as soon as you can. Okay. At the end, actually, I do throw in some bonus. Yeah, I'm going to throw. I know on the final homework. On the final homework, I'm going to throw out some bonus. I got to figure out exactly what problems they're going to be. But last year, what I did was I threw in 4 bonus problems, and I had them. I assigned them at the same time as problem set number 6. And so those were basically extra problems you could do to boost up your homework grade. It will boost up your overall grade. So, and I think it was worth like half a problem set worth. All right. Any questions before we get started? Yeah? All right. So today is D-Day. We're going to be talking about eigenvalues. And this is going to lead us into a discussion about Green's functions. Okay, so did anybody get a chill when I said Green's functions? Okay. Okay, so those are the people who have some familiarity with Green's functions. For the rest of you, you'll be scared later. So, anyway, this is probably the topic that is the most confusing to students throughout the entire course, and so this is one of those things where, you know, part of my philosophy on teaching advanced topics is that it's almost like a time-delayed drug or grenade or something like that, where I'm putting this into your brain and it's going to go into your subconscious and it's going to marinate for a while, and then sometime, you know, it could be a few weeks from now, it could be a few months from now, it will just kind of jump out and you'll understand what's going on. Okay, could it also be a few years from now, but it should happen eventually. And Green's functions are one of those topics where it's not extremely difficult, but it's just that the way they work is a lot different than other things you've seen, and they're very useful, and you'll see why. So the basic idea here is that you've already seen simple eigenvalue problems. An example of that is mv equals lambda v, where v is the eigenvector, lambda is an eigenvalue, and m is some matrix, right? And so what you'll do is you'll say, let's say we have a matrix which is just made up of ones. Then when you're solving this, and this eigen vector is just a two-component vector. And so what happens is you end up having this equation where you effectively have 1 minus lambda times v1 plus v2 equals 0, and v1 plus 1 minus lambda v2 equals 0. And you would just basically take the determinant of m minus I lambda, which is basically taking the determinant of 1 minus lambda, 1 minus lambda, 1, 1. And then when you calculate this determinant, what you'll find is that you have 1 minus lambda squared minus 1, and this is going to have values of, let's see, 1 minus 2 lambda plus lambda squared minus 1. These two cancel out, and you have lambda times lambda minus 2. And then the answers to that are lambda is equal to 0 or 2. So that's your two eigenvalues. And then if you plug these eigenvalues into here, then you have v plus v2, or v1 plus v2 equals 0, and v1 plus v2 equals 0. So v1 is equal to minus v2. And then you have the other one, lambda is equal to 2, so you have 1 minus 2, which is negative v1 plus v2. and then you have V1 minus V2, both are equal to 0. And so this is the answer, V1 equals V2. And so you end up with two eigen values. One is 0. Actually, I should write this better. Lambda 1 equals 0. And that gives you the eigenvector V1 is equal to 1 minus 1. I didn't normalize it. And then you have the other one, lambda 2 equals 0. And that gives you an eigenvector of just 1, 1. Non-normalized. Or sorry, I didn't. Mouth is faster than the hand sometimes. So this is basically an eigenvalue problem. We have our matrix or operator. We solve for the eigenvalues, and then we plug those into this equation and we solve for the eigenvectors. And now we have eigenvalues and eigenvectors. And if you multiply these two eigenvectors together, you'll see they're orthogonal to each other. Right? Now, you'll notice here a couple things. First off, that this is actually a homogeneous problem, because you can see that you can write it as mv minus lambda v equals 0. So each term involves the v on here. It's homogeneous in the same way that when we looked at ODEs at the first week, we saw that, if you had the 0 on the right-hand side, we called it a homogeneous problem. So this is a homogeneous problem. The second, and because this is a homogeneous problem, we can only determine the eigenvalue up to some arbitrary constant. If we multiply, this is not normalized, but it works. And you can show that they're orthogonal to each other. But you can multiply these by 5 or 10 or 100, and they still work, right? So, and the idea is that that's because this is a homogeneous problem. Another thing you'll notice is that we could have an inhomogeneous form of this. And an inhomogeneous form would look something like mv minus lambda v equals u, where u is not equal to 0. This would be called inhomogeneous. And if this were an inhomogeneous problem, then lambda would not be an eigenvalue and v would not be an eigenvector in order to solve this problem.
So by homogeneous or homogeneous, you mean, that doesn't mean like uncoupled, or does that mean like the V1, V2 aren't, I don't understand what, I'm sorry, I don't understand what homogeneous is.
Okay, homogeneous in this case means that you have the eigenvector is multiplying every term. So everything in here comes in with the eigenvector. So in other words, and I can show you easier with differential equations, and we're actually going to get to that a little later. But yeah. No. Well, I mean, because all of these eigenvalues are going to be equal. But homogeneous in this case means that there is no term in here which is not a direct function of the eigenvalue or eigenvector. So because u is not the eigenvector, this is inhomogeneous. If u was the eigenvector, and you could actually combine it over here, then you could say that that's homogeneous.
So homogeneous means it's essentially a one-to-one map to the eigenvector.
Mm-hmm. Yeah.
So like if I were to write the original equation up there for an inhomogeneous one, like you have m times v equals lambda times v. For an inhomogeneous equation, that would be m times v equals lambda times v plus u?
Yeah.
Okay.
Yeah.
All right. Another thing you'll notice here, and this is like I stated last week, the dot product of the eigenvectors is 0. Eigenvectors are orthogonal to each other. That's a non-negotiable fact of an eigenvalue problem. And finally, an arbitrary two-component vector can be written as a linear combination of eigenvectors. And what that means is that in this case, u is not the same as v. But because u is a vector, or assuming u is a vector, then u can be written as a linear combination of these. Okay? And this is why these eigenvectors form a natural basis for doing other mathematics, or forming a natural basis of your system. So this is a very powerful thing in eigenvalues and eigenvalue problems. And when it's something that's this powerful, you know that you're going to be seeing a lot of it. So that's where you got to pay attention. And so what I'm going to show you now is an eigenvalue problem, which is written, instead of using matrices, I'm going to actually use differential equations, but it's going to still be an eigenvalue problem. Okay? So in this case, let's suppose we have a vibrating string. And by the way, anybody that's been paying attention in physics classes, you know that you're always going to see harmonic oscillators, because that's one problem we can solve exactly, and that's what we use as a model in nature over and over and over again. And so we're going to fix the string at x equals 0 and x equals L. So in other words, you picture a string. Here's x equals 0, here's x equals L, and here's your string, and then you go in and you pluck it with your finger, and it vibrates. So it can vibrate like this. It can vibrate like this. It can vibrate like this. It can vibrate all kinds of ways, right? So the differential equation describing the vibration is going to be where u is the amplitude of vibration. Is going to be this, where k is the wave number of the string. K is actually going to be equal to the angular frequency of the string divided by c, which is the speed of the wave in the string. It's not the speed of light here. And so what happens is, this is the differential equation which is describe what the string is doing. And we know this is the differential equation because we know the equation for the force on a string, right? If it's elastic like a rubber band, then remember that the acceleration, or mass times acceleration, gives you force. And if you take your the k term, or the times that mass times the amplitude, that's also going to be force. It's going to be restorative force.
So dE is the distance between the endpoints, and L is the length of the string?
No, these are derivatives.
No. The top
Oh, here?
Yeah, what's
Oh, no, that's 0. Sorry. That's supposed to be a 0. Oh, it's fixed at 0 and L.
Like a 0 and L?
Yeah, just 2 points, it's fixed at.
Okay.
Yeah, that's just understanding my my writing. Okay, so we got this differential equation which is going to describe exactly what's going on with the string. And this you can get from physics as far as forces go. So what's going to happen is, if you set u equal to 0 at x equals 0, this is a reasonable thing to do because you know it's fixed, and you know that the amplitude will say it's 0 at x equals 0. Then what happens is you can say, well, the solution to this is u equals a sine of kx, right? Because you take the second derivative of this, you're going to get k squared times minus u, right? Which fits into the differential equation, and it works. That's a standard solution to the ODE. Now, we also want u to be equal to 0 at x equals L. And you know if you set x equal to L, and you want u to be equal to 0, then you have 0 equals sine of k times L, and therefore you get that k must be equal to some integer times pi over L, right? Where that integer can be equal to 1, 2, 3, whatever. And so what happens here is that there is not one single answer that works. It's basically any solution that you come up with, as long as you're using k equal to m pi L, and this is a sine function, is going to fit this problem, right? Can everybody see that? Because it's going to fit those same boundary conditions all the time. Now, here's the neat thing. If we're going to put this into the language of eigenvalues, then k is an eigenvalue. And you notice here that these eigenvalues, k, you can also call k squared or minus k squared an eigenvalue, because you can see that k here fits into the eigenvalue problem exactly the same place that lambda does in the other equation. These two look very similar, right? Only this is an equation involving matrices and vectors, and this is involving a differential equation. So u is an eigenfunction. Because it fits in the same place as the vector did before, but we can't call it an eigenvector because it's obviously not a vector. And then this derivative here, that is our operator. And it is linear. So we have a linear operator, we have an eigenfunction, and we have an eigenvalue. So this is still an eigenvalue problem. The only thing is that in order to turn a differential equation into an eigenvalue problem, you have to have well-defined boundary conditions. That's the only thing you need. And then if you set these well-defined boundary conditions, now you can say that this is an eigenvalue problem. And just like anything else, you can see that, well, the eigenvalues are very discrete. There's many of them. There's actually an infinite number of eigenvalues you can have in here. But each eigenvalue corresponds to an allowed wave function between those 2 points. In the eigenfunction, you can see those are sine functions. And I'm actually going to show you later on that these are actually orthogonal as well.
So just on your boundary conditions, how did you get, you got the sine functions just by solving the differential equation. That's what the solution is.
Yeah.
Okay.
Yeah. And we just have to say what the boundary conditions are. Because the thing is, if we didn't assign boundary conditions, then you couldn't have this well-defined thing. And the neat thing here is that, and this is kind of going back to what we talked about Fourier series, we can basically add up every possible solution for u, and that's where this coefficient a comes in. It's to say, well, one particular value of u is greater than another one or something like that. We could even parameterize a with this m, so we know what mode we're talking about. And we can actually add up all the different possible values, all the different solutions that fit those boundary conditions, add them all up and say, well, that is the overall solution to our problem. Kind of like we did with ordinary differential equations. Let's say the sum of all possible solutions is the solution. And so by doing that, you create a space of eigenfunctions which forms a complete set of all possible solutions to your system, the same way that eigenvectors form a complete basis to describe your coordinate system of your problem. The only real difference here is the fact that in this first example, you had two solutions. For this one, you got an infinite number of solutions. Otherwise, they're the exact same.
Are the K's the same in there? K squared at the beginning and then K at the time?
Yes. Yeah, the K is the same. That's why I could argue that instead of calling K the eigenvalue, you could say K squared is the eigenvalue or minus K squared.
Yeah.
I mean, it might be more technically correct to call K squared the eigenvalue, but it works.
So we use pretty much the Green's function.
No, we're not to Green's functions yet.
The equation is perfect.
Yeah, what we'll find out is the Green's function comes in when we're dealing with an inhomogeneous system. As long as it's a homogeneous system, we're just strictly talking about eigenvalues and eigenfunctions.
How did you physically represent
How to physically represent what?
Because you say U is 0 at X. It's 0.
At X equals 0.
It's like the height of the string.
Yeah. Yeah. So, I mean, in between, U could be some non-zero value. So U could be however big you want the amplitude of the string to go up to. But it just has to be 0 at those boundaries. If I had changed the boundaries, then that would change the problem and that would change the eigenvalues. Like, let's say U was equal to 0 at 0 and 2L instead of L. Then all of a sudden your string is twice as long, and that means that all of a sudden you've got solutions that are going to apply that don't apply here because they can literally be twice the wavelength. Like I said, this is really interesting and really powerful, and this is really the basis of what we're going to be talking about here. So, in general, what we could say then is that if you take some linear operator times some function, it's equal to the eigenvalue times that function, and then that function is the eigenfunction. And we're going to say we have a region which we're going to call omega. And omega is going to have certain boundaries on it. So we're always going to have this is going to be our region of interest. Then what we'll say here is that L is Hermitian if you integrate the complex conjugate of U as a function of position times the linear operator times V, which is a function of position, over your region of interest. And that ends up being the same thing as if you take your integral over your region of interest as a complex conjugate of V times L times U. And then take the complex conjugate of this whole thing. Okay, where here U and V are eigenfunctions. Now, can anybody remember why Hermitian is a big deal? Yeah, but why? You're on the right track. You're almost there. The reason why Hermitian is important to us in physics is because if you have a Hermitian operator, it always yields real eigenvalues. And real eigenvalues can be observed because we can't observe anything that's imaginary. You know, Yeah, like energy is an example of a real observable. And to get the energy out, you have to have energy shows up as an eigenvalue and of the system. And actually, this is kind of a good parallel here. When we're talking about quantum mechanics, this is exactly how quantum mechanics works. Quantum mechanics is basically taking the real world and reducing it down to operators and differential equations with well-defined boundary conditions, and then saying that everything we observe is an eigenvalue. And if those are not real eigenvalues that come out, then we can't really observe them. You know, we can talk about, Superman, the Easter Bunny, and Santa Claus all we want, but those are not observable because they're not in the real regime, right? Yeah. So what's going to happen here? Sorry if that offended anybody. A little bit. Yeah. Okay, I'm sorry. Okay. Well, the other two. All right. So anyway, the thing is here is that we want to be able to get something real out, and so in order to get something real out, we have to use the Hermitian operator in order to say that we're going to get real observables out. So therefore, when we're doing physics, if it's not Hermitian, most of the time, unless you have a really good reason to keep that operator, it's probably not going to correspond to anything you're going to actually do.
This applies to like physical activity, you deal with two different surface points in the eigenvalue that you deal with two different observables.
Yeah, that's a good question. And I think that's where you start getting into like quantum theory of gravity or quantum relativity, because and people have looked at that where there was actually an idea that came out a few years called doubly special relativity, where it's special relativity of one invariant, which is the speed of light, and in doubly special relativity put in a second invariant, because of the simple fact that if you have this extra invariant, now you can agree on things like boundary conditions, and then you can quantize the system effectively. But yeah, I mean, good thought. It's an interesting thought. It's just not easy to actually apply. So anyway, so we like these eigenvalues and we like real eigenvalues. So what we can do is, let's suppose if you take the linear operator and you have this eigenvector, it produces an eigenvalue times the eigenvector. And also, if you get the same thing for an eigenvalue of j, or eigenvector j, then that gives you a different eigenvalue times uj. Okay? So this is the exact same way that eigenvectors and eigenvalues work when we're talking about matrices. The difference here is that these are not matrices, and also you can see that I and j are different, just like they are in the vector sense. So what happens then, if we have this Hermitian condition here, then you could see that if you take the integral over your area of region of interest of uj complex conjugate, I'm going to leave off the coordinate L acting on ui, and you integrate this over the volume, then this is going to end up, when you take the linear operator and you have it acting on your eigenfunction, you're going to end up getting out the eigenvalue. And the eigenvalue is just a scalar, so it can actually leave the integral. And now you have your integral over your region of interest, uj complex conjugate, ui integrated over the volume. Okay? Now if you do the same thing, but you use the order flipped on them, so you have ui complex conjugate L U J, then when you do this, you're going to get lambda J, a different eigenvalue out, and you're going to have this integral here. And then let's do it UI complex conjugate UJ. Okay? Okay, now our Hermitian condition up here basically says that if I take the complex conjugate of this whole thing, that it will be the same as if I just flip the order of U and V, effectively, right? So what I'm going to do is I'm going to take this first equation, and then I'm going to subtract off the complex conjugate of the second equation.
Is that UI?
Yeah, this is UI UJ. Yeah. I think that's a little bit more clear. So if I take the first equation, I subtract off the second equation, then what I should have is lambda I minus the complex conjugate of lambda J, and then both of these are being multiplied by the integral over omega of UJ complex conjugate UI integrated over value, right? And so this works because you can clearly see that if I take the complex conjugate of the second equation, it looks like the first one except for the eigenvalue is different. And according to this equation here, this should yield 0 if I do that. Now, this is a very, very powerful statement here, because what happens are two things. Let's suppose that I and J are the same, are different than each other. Or let's suppose I and J are the same first. If I and J are the same, then I basically have lambda I minus the complex conjugate of lambda I, right? If L is Hermitian, then the complex conjugate of lambda I is equal to lambda I because they're only real eigenvalues, right? So what I get is that if I is equal to J, this is 0, obviously. But what about if I and J are not the same? What if they're different? Then it makes sense that I have different eigenvalues coming out. So lambda I minus lambda J should not be 0. In which case, that means that this integral must go to 0. Right? And that is the definition of orthogonality for eigenfunctions. So what that means is basically, yeah, I'm going to, trust me. So what happens, what I just said was, if I and J are the same, because this is Hermitian, is the condition where this is equal to 0, then if I and J are the same, then lambda I minus lambda I are equal to 0, because the complex conjugate of lambda I is equal to lambda I. Since if it's Hermitian, they're real eigenvalues, and therefore taking the complex conjugate doesn't change anything, because there's no imaginary part. But if I and J are different, okay, because they're different eigenvalues, now all of a sudden lambda I minus lambda J are not 0, and the only way this can give you 0 is if the integral goes to 0. Okay? And so the integral going to 0 is the definition of orthogonality, and that's the same thing as if you take two eigenvectors and you take a dot product of them. So what happens effectively is that if you have u dot v, and u and v are both eigenfunctions, that's equivalent to taking the integral of the complex conjugate of u and v and you take the integral of that over the region of interest and you get 0. And those are called orthogonal functions. And so an example of orthogonal functions, can anybody give me an example of something that would do that? Right, sine and cosine. That's a great example. And actually, that is how Fourier series and transforms work. Is if you think back to it, and like I said, this is why the class is structured in this way. You've already been through all this muck, so you can kind of look back on it, reflect on it now. But when we did Fourier series, remember we had this thing where you had the sines and the cosines, and you're trying to find the coefficients, and you know if you multiply on the sine and you integrate over the boundaries, then it goes to 0, unless you have the same frequency, the same M value in both. And the reason why that happened was because sines, cosines are orthogonal functions. So if you take the integral from, say, 0 to L, and I'm going to use the example from before with my u. So I have sine of m pi over Lx times the sine of n pi over Lx dx. That is equal to 0 if m is not equal to n. And you can prove that, right? If I put a cosine in here instead of a sine, you get the same result. So sines and cosines form a complete set of orthogonal eigenfunctions. And because they form a complete set of orthogonal eigenfunctions, that's why you can expand out any periodic system in terms of these orthogonal eigenfunctions. And really what you're doing when we're doing Fourier series, what we were really doing is we were solving eigenvalue problems. They just never tell you that when you learn this stuff the first time. So what you were really doing was you were solving this eigenvalue problem where it's periodic boundary conditions. So you had your well-defined boundary conditions. Your eigenvalues that you were getting were those coefficients, they call them, where you had, you had your n equals 1, n equals 2, n equals 3, whatever, for your Fourier series. And then you had your, you had your coefficients in front, the a's, which corresponded to a specific m value, or n value. And all of them were orthogonal functions, and so they formed a complete set, and then you had your answer. Does that make sense? Okay. I kind of put some things in perspective you guys may have seen a little bit differently before. Yeah, it's orthonormal if they're normalized and they're yeah. So I mean, when we talk about orthonormal, that applies more when we're talking about eigenvectors. With eigenvalues, eigenfunctions, it's difficult because normalizing this stuff is not easy when you have an infinite number. So trigonometric functions are basically a set of periodic functions. And so you could take, for example, our string. Then you have x going from 0 to 2 pi. And u of 0 equals u of 2 pi, which is equal to 0. And also, when you take the derivative of u at 0, is equal to the derivative at 2 pi. This is the definition of periodic. It's basically saying that your solution and your derivative are the same at the boundaries. So what happens is we can ask ourselves the question, is this a Hermitian operator? And you can find it by just simply going, well, we integrate from 0 to 2 pi of the complex conjugate of u times the derivative, second derivative with respect to x of v, or sorry, of v dx. And then what happens is that this, we do integration by parts, and you have complex conjugate of u dv dx evaluated from 0 to 2 pi. And then you have the same solution at 0 and 2 pi for both of these, so that's 0. And then you subtract the integral from 0 to 2 pi of the derivative of u with respect to x, the derivative of v with respect to x, dx. And then you do integration by parts again, and you end up with another term minus du complex conjugate dv, or dx, times v evaluated from 0 to 2 pi. Again, that goes to 0 because of periodicity. And you have from here, you have the integral from 0 to 2 pi of v times the second derivative with respect to x of u complex conjugate dx. And then what happens is you could say, well, this is equal to taking the complex conjugate of the entire integral, complex conjugate v, second derivative u dx, like this. And that is the definition of Hermitian, right? And so because of this, we could say, well, this is a Hermitian operator. And it's Hermitian. It gives us these real eigenvalues, which we use for our sign, and gave us the basis of creating these Fourier series. And of course, if you could do Fourier series, and you could do Fourier transforms as well, which is the whole point of this. And the neat thing about this is that this means that anything that you can, anytime you can form a set of orthogonal eigenfunctions, you can form something like a Fourier series. So all the special functions we're going to talk about in a few weeks, like Bessel functions and spherical harmonics and Legendre polynomials, all that stuff, you can use those to form something akin to Fourier series. And what this is good for, especially if you're doing numerical work, is it basically says that if you have those same fixed boundary conditions, you can look at every possible solution with a boundary condition, and you could use that to break down whatever your solutions are to the system, and use that as a way of kind of solving what's going on, by just sort of fixing which eigenvalue terms are going to be higher or lower. All right. Any questions so far? This is interesting, hopefully. All right. So next thing I want to talk about is another example where we're going to use the Stern-Liouville differential equation. All right, so here you've got the derivative of some function of x du dx, where u is a function of x, minus q of u plus lambda rho of x u of x equals 0. Okay? In this case, p, q, and rho are all real functions. And also rho is assumed to be positive. Okay? And so what they do is u of x is equal to 0 at the boundaries. And you have to say rho of x is greater than 0. And so what happens is you end up with, if you look at this differential equation, it looks kind of ugly, but you can pick out an operator here, where the operator is essentially p has a second derivative with respect to x plus p prime times d dx minus q. And all of that, if you apply it to u, is going to give you your linear operator. And then rho is this extra term that kind of fits in here with the eigenvector, or sorry, eigenvalue. And so what happens is your orthogonality condition, and you have to do a little bit of math to see where this is coming from, is basically going to be that ui dotted with uj is going to be defined as the integral over, say, a to b of ui complex conjugate of x uj of x times rho of x dx. And this is for I not equal to j. And so what you can do is you can actually normalize the eigenfunctions in such a way that when you take the dot product you get 1, and that would be your normalization. And this is one of these things where we don't really have a lot of time to talk about it in class, but you can basically go through what we did before and show that this must be true, that this is the orthogonality condition. All right, now what we can do now, and this is actually going to take us into Green's functions. And so what I want to do, it's only 5 o'clock, so I would like to just continue on and just work through Green's functions if you guys don't mind. And then after we get started on that, then we'll probably be finished a little early. But the idea now is that since we have this orthogonality condition, where you can basically say ui dot uj is equal to just taking this integral of ui uj of let's say rho of position gives you your delta function. Now, what we can do is we can actually take advantage of these eigenfunctions, especially when they're normalized, and use that to actually understand what's going on with other functions in our system. And this is going to lead us to a way of actually solving even inhomogeneous problems. So the idea is that because we can expand our any function in terms of eigenfunctions, let's say we have an arbitrary function f of x, we can write that function as a sum over n of c sub n and u sub n of x. Where what we're doing is we're taking all these orthonormal values of u sub n, all these normalized values, and we're going to sum them up with the appropriate coefficient in front. And by doing that, we're going to retrieve whatever function we're talking about. And this is very similar to a Fourier series, if you think back to that, where any type of periodic function you can have, you can expand out in terms of sines and cosines, where all the sines and the cosines at the different frequencies are basically just orthonormal functions. And so it's, literally the exact same thing. So now, if we could expand out this to give us a function, then if we take an eigen function and we dot it with this function f, then that is the same thing as taking the sum over n of c sub n u sub n dotted with u sub m, which in turn is like the sum over n of c sub n and a delta function of n and m, which is just going to give us c sub m. So in other words, we could find our coefficient that we needed by just taking the dot product. And this is the exact same operation where we found the coefficients in our Fourier series, just written in a different way. So f of x can also be thought of as if you take the sum over n of u sub n, and you have that times u sub n dotted with f, because you end up with this delta function which recovers your f again. This I can expand out as the sum over n of u sub n of x, and then this dot product is the integral of, and assume I'm integrating over a value of u sub n complex conjugate of x prime and f of x prime and rho x prime. All right? Now, this, we can actually, since this is a function of x and this is a function of x prime, we can take the sum and move it inside the integral. So now we have the integral of f of x prime, and now we have rho of x prime. And now I'm going to move these two underneath the sum. Okay? And so what happens is all of this has to be a delta function, because we have to recover back our f of x. And so this is a completeness or closure property of these things. And so what's happening now is I basically just said that I can now define any arbitrary function which obeys the same boundary conditions in terms of my eigenfunctions, which again is the way a Fourier series works. So, how does this help us solve inhomogeneous equations? Well, I'm glad you guys asked. So, you take your inhomogeneous equation, okay? And an example of an inhomogeneous equation could be you have a nice wave equation, but then it's spoiled by some term on the right-hand side that doesn't quite fit in. to what you like. It's not 0 on the right-hand side. And so a wave equation where you might have a driving or forcing term is a good example of that. So you have this inhomogeneous equation where if f was equal to 0, this would just simply be an eigenvalue problem. You're done. It's easy. But because f is non-zero, now things are a little more complicated. Now, you know that this thing has certain boundary conditions, and L is Hermitian. But because f is non-zero, these are not eigenfunctions, and this is not an eigenvalue. So what you can do is you can expand this term on the right-hand side in terms of L, in terms of the eigenfunctions. And you can expand this u, which is not an eigenfunction, in terms of eigenfunctions. Because everything exists in the same space of eigenfunctions. So I can say that u of x is equal to the sum over n of c sub n u sub n of x. And f of x is equal to the sum over n of d sub n u sub n of x. Okay? So now, if I do this, I can say, well, this is equal to the same thing as L of u of x is really the same thing as the sum over n of c sub n and then L acting on u sub n of x. Right? Can I do that? I can do that because it's a linear operator, right? And a linear operator, remember, can go inside of the sum, and it can act on each term in the sum individually, the same way it acts on all of them collectively. So when I put my linear operator inside of this summation, what happens is I end up with the eigenvalue. So this is sum over n of c sub n, lambda sub n, u sub n of x. So now I can take all of this and I can put it back into the original equation, and I have the sum over n of c sub n, lambda sub n, u sub n of x minus lambda times the sum over n c sub n, u sub n of x is equal to the sum over n d sub n u sub n of x. Right? So everything is now expanded out in terms of eigenfunctions. So now everything is being summed over n, so I can pretty much ignore all the summations. And I can also combine a bunch of this stuff too. So I have u sub n's are the same everywhere. And so I could call this, let's see, sum over n of c sub n, lambda sub n minus lambda, u sub n of x is equal to the sum over n d sub n u sub n of x. And then same summation, so I could just ignore that. Same u sub n, I could ignore that. And I'm just left with c sub n is equal to d sub n over lambda sub n minus lambda. But d sub n is also equal to u sub n dot f, because if I take my f of x, my f here, and I dot it with u sub n, and they're orthonormal, then I end up getting my coefficient back. So therefore, I could say that c sub n is equal to u sub n dot f over lambda n minus lambda. And once I know what my c sub n is, then I know what u sub n is, which is my solution that I'm looking for. Because the whole point of this thing was to find u of x, which is my solution to my problem. And so what this is telling me is, if I know what f of x is, which is given in the problem, I know what my eigenfunctions are, which I should be able to find, right? I know what lambda is, which is given in the problem, and I know what my eigenvalues are. I can find my solution. So my solution, u of x, is equal to taking the sum over n of u sub n dot f divided by lambda sub n minus lambda. And you can write that out, expand the dot product. So this is u sub n of x times lambda sub n minus lambda times the integral over my region of interest of u complex conjugate sub n of x prime times f of x prime d cubed x prime. So basically, if I could just take all the pieces and put them together, then I know my solution. And another way to write this is to say that u of x is equal to the integral of g of x and x prime, a function of x and x prime, times f of x prime d cubed x prime, where g of x and x prime is equal to the sum over n of u sub n of x complex conjugate u sub n of x prime divided by lambda sub n minus lambda. This is known as the Green's function.
Where did your lambda sub n come from? I thought it was a 1.
Oh, no, it came from right here. It came from this first thing right here. Remember, and it came about because we applied our linear operator inside. Yeah. So essentially, the Green's function is a magical tool that if you know what it is for your linear operator and your boundary conditions, and you plug it in to an integral with whatever that junk is on the right-hand side that's just screwing up the homogeneity of your problem, it magically gives you the solution. So if you know the Green's function, you pretty much solve the problem. If you don't know the Green's function, then solving and finding the Green's function is the tricky part. And this is actually very, very, very useful, like in electrodynamics. If you look at the equation for finding, for solving the Poisson equation, and actually I think I'm going to do this on Thursday, is when you're trying to find the solution for potential outside of a charged particle, and you have that formula that they always show you where it's kind of like the potential is a function of x is equal to, it was like integral of x, rho of x over r dx, or sorry, it's x prime. And I think, what was it, 1 over 4 pi epsilon, 1 over 4 epsilon naught, 4 pi epsilon naught? Yeah. So it was basically this equation. This is actually the solution to a Green's function equation. This is a solution to a Green's function, where the 1 over r here is the 1 over 4 pi gives you the Green's function. Well, the 1 over 4 pi r gives you the Green's function.
I think I have that explanation.
Yeah. Well, they also write it like this, where they might have, instead of saying R, oftentimes you'll see this written as, it'd be x minus x prime magnitude. Yeah, same thing. And when you write it like this, it really looks like a Green's function, because it's a function of x and x prime. So that's just a practical example how you use the Green's function, and then you'll see it all over the place in other physics. And remember, since the idea of quantum mechanics is everything turns into an eigenvalue problem, then you got to assume that you're going to eventually end up with some inhomogeneous problems too.
You definitely use Green's function in psychology.
And we use this in general relativity with gravitational waves. So this actually shows up in a lot of places throughout physics. And it shows up because the world is not that neat and tidy that everything just kind of fits into a box. And so in order to determine your Green's function, you need a differential operator, a particular region of interest, and suitable boundary conditions. So you can't just have a Green's function with no boundaries. And when I say suitable boundary conditions, that's not saying you have to have boundaries at A and B. You can have boundaries at 0 and infinity, and that could be suitable. Like in this case, to find the solution to the Poisson equation, and this basically came from solving this equation, right? Everybody remember this? So this is the problem that you solved, and that was the solution to it. It's just that in pretty much every physics class you've had, they've never really shown you how they make the sausage here. They just kind of skip right to it. But yeah, you can use it here. Like I said, you can. It's used to calculate like gravitational waves, Chris. And so it's very, very useful, and it crops up a lot. So I think most of what we're going to be doing for the rest of today is going over more and more with the Green's functions and a few examples on how we would solve them, and and just there's a lot of different ways of actually calculating the Green's function. And so what I'm going to do is I'm going to go over the examples. This first thing I showed you here is a very useful tool for understanding how the Green's functions are constructed and what they actually mean, but they're not really as practical to work with because this Green's function is an infinite series. It's not an analytic function, and integrating that can be a pain in the butt, although it is an acceptable solution. So what happens is we might have f of x equal to, or f of x prime equal to delta of x prime minus x naught. Okay? In this particular case, when you solve for your function, your solution, and you're integrating your Green's function, where you're literally integrating it with the delta function, right? And so when you do that, the Green's function is literally your solution. So the Green's function is the solution to your problem when you have just a delta function on the right-hand side. And that's just a good thing to know. And what that means is that if you have a non-zero solution on the right-hand side. If you replace it with a delta function, then, and if you somehow solve the differential equation, then your solution is the Green's function and you're done. So that gives you one way of actually solving the problem. And so what you should also note from this construction thing I showed you here is that if lambda equals lambda sub n, then you end up with infinity here, right? But that would mean that you don't have an inhomogeneous solution. You actually have a homogeneous solution, in which case f is equal to 0, and you don't need a Green's function anyway. So this kind of corrects itself for any problems like that. All right. So let me give you an example going back to the wave. So we've got a string of length L and it's vibrating with some angular frequency. So we have the second derivative of u with respect to x plus k squared u is equal to 0, where u of 0 equals u of L, which is equal to 0. And k is equal to omega over c, like we had before. C is the velocity of the wave. So there are different methods of solving the Green's function, and I'm going to start off with what I'm going to call the first method. And that is going to be construction. So in the construction method, what we're going to do is we're actually going to construct the Green's function, where the Green's function is actually going to be constructed by finding the eigenvalues and eigenvectors and then plugging them into this equation. So when we do that, we have, we're going to say that k squared is equal to minus lambda. And so now our differential, our equation is basically going to reduce to something like this if it were homogeneous. And so this is like the homogeneous version of our equation. So now we have eigenvalues of lambda sub n, which are equal to minus n pi squared, or n pi over L squared, where n is equal to some integer. And eigenfunctions are going to be normalized so that u sub n is equal to the square root of 2 over L times the sine of n pi x over L. Okay? And so the Green's function in this case is equal to 2 over L times the sum over n of the sine of n pi x over L times the sine of n pi x prime over L divided by k squared minus n pi over L squared. And so what happens here is, you can see this is an infinite series. It actually looks a lot like a Fourier series in some ways. And so this is the Green's function. And you can see that if you take the complex conjugate of the Green's function, you get itself back, because the whole thing is real. Okay? And so this is one method of finding the Green's function. It'll give you a solution. How useful that solution is kind of questionable, though. But at least you got something, right? Now, then we have the second method. And that is where we're actually going to use the fact that if we had a delta function on the right-hand side, then this would result in, this solution to this would be a Green's function. And so this is the same thing as a vibrating string where we have a point of force that is right here. In other words, imagine for a minute you're playing a guitar, and you know, if anybody's ever played a guitar, you know how it's got the bridge in the middle of it. And the way you play the guitar is you strum the strings, cause them to vibrate. But then there's a fixed point at one end and there's a fixed point at the other end. But in between, that's where your finger is, right? So your finger on the guitar, you're not just simply making the strings longer and shorter by pushing your finger down on it. You're actually creating a Green's function solution, because you still have part of the vibrating string on one side of your finger and another part on the other side, right? So what you're doing is actually this exact same physical property. So what we can do in this case is that we can look at having x prime is the location where the finger is on this vibrating string. And you can see that you basically have two parts to your Green's function solution. One part is going to be where x is less than x prime. In other words, from 0 to x prime. And in that part, you know, delta, the function is 0 on the right-hand side, and you just have an a sine of kx is your solution there. On the other part, you got b sine of k times x minus l. And this is for x greater than x prime. And so what happens here is at x equals L, you got 0. And so this matches up with the boundary conditions on both sides, right? Everybody agree? So what's going to happen is that you need this function to be continuous at x equals x prime. And the way you do that is, well, we'll say if you, G is the solution. If you take the derivative of G with respect to x, then what you'll see then is that you're taking the derivative of this entire equation in order to see what that is. And so what we'll do is, let's see, we know that this equation reduces to g double prime plus k squared g is equal to the delta function, right? And then if we were to integrate this thing across the boundary, what happens is we integrate this entire equation between x prime minus epsilon to x prime plus epsilon, where epsilon is a tiny, tiny number. So we're integrating it right across the boundary, and we end up with g prime here. Now g should be continuous across the boundary, so if you integrate that across the boundary, that's 0. And then the delta function here is going to give you 1, right? So we're going to evaluate this from x prime minus epsilon to x prime plus epsilon, and this is going to be equal to 1. And the reason why is because if you remember, if you integrate a delta function across that delta function, you're going to get 1. Does everybody agree with what I came up with here? Yeah. And it's all because when you evaluate this integral of the g across the boundary, it's continuous. Yeah, because g evaluated from x prime minus epsilon to x prime plus epsilon is equal to 0. Okay? So, and you can also see that this is true because if you integrate this guy again across the boundary, then you're going to get the same thing, right? Because you integrate this guy, you're going to get g evaluated across the boundary. You integrate 1 across the boundary, it's 0. So what happens then is we could say that if you take this, what it means to us when we evaluate that is that g prime of x prime plus epsilon x prime minus g prime of x prime minus epsilon comma x prime is equal to 1. All right? There's a discontinuity in the first derivative. And so what we can do is if we take the derivative of this guy, we get g prime of x and x prime is equal to taking the derivative of this, which is going to be, let's see, a k cosine of kx for x less than x prime, and b k of cosine of k x minus L for x greater than x prime. And so what I'm going to do is, given the fact that we know that g is continuous and the derivative of g is not continuous across the boundary, I got a set of 2 equations. The first one is going to be from g being continuous. I'm going to write it like this. And that's going to tell us that we have a sine of kx prime is equal to b sine of k x prime minus L. And then you have g prime equals 1 across the boundary, and that is ka sine of k, cosine of k x prime plus 1. And then you have, because I'm evaluating this thing across, and then I have the other one, kb cosine of k x prime minus L on the other side. And so I have 2 equations and 2 unknowns. Because my 2 unknowns are a and b, and I have these 2 equations, which I need 2 equations to solve. And so if I simultaneously solve those, I get a equals sine k x prime minus L divided by k sine of kl. And then the other one is going to be b equals sine of k x prime divided by k sine of kl. And so from that, I get that my Green's function is equal to 1 over k sine of kl times the sine of kx times the sine of k x prime minus l for from 0 to x prime. And then for the other one, I have sine of k x prime, sine of k x minus l for x prime to x to l. And so you can see that this is a little bit of an improvement over what we did before. And there, there's some shorthand ways of doing this too. But the idea here is that I was able to. Right here?
Yeah.
It's been a while since I simultaneously saw these, but I think.
Right, you divide them both by sine k prime kx prime.
Oh, let me see. Okay.
Sorry, you're being
I think when you're solving these simultaneously, you need to see I think we needed to take advantage of yeah, I'm not gonna worry about it. It's anyway, it comes out in the algebra. It should come out in the algebra. But the big thing here is that we went from before we had a system where we had an infinite series and with an infinite number of terms, and now we're down to 2 terms. So on the negative side here, we have a Green's function solution which is discontinuous, where you literally have one solution up to one part and another solution up to another part. So this is more usable than the other one, but it's still not perfect. And the way you would actually use this is like if you were to integrate, you would actually integrate from like 0 to x prime, and then from x prime to L in 2 different integrals in order to solve your equation, and then add those together. So, like I said, far from perfect, but it works. All right, now the next thing I want to talk about, and this is sort of like this last method, is what you would do if you're talking about electrodynamics. And so this is where you have Laplace's equation, which is if you take the Laplacian of your potential, you get 0 if you're in a vacuum. You have boundary conditions, which is your potential. Your potential has to be equal to 0 as r goes to infinity. That is your only real boundary condition. If you put in a source charge, then you could model your source charge as a delta function, and you have something like this, which basically what happens is your potential goes to infinity as you get to 0, and then as you go infinitely far away, it drops off to 0. So what happens is you're really saying that you have your potential which is a function of r, which is like the potential is a function of the magnitude of x minus x prime. And so if you have x not equal to x prime, which means you're not at the location of the origin. And by the way, normally the way this is used in classical electrodynamics, not quantum electrodynamics. And so in classical, you can have point particles and you can go pretty much right up to the particle and not have weird things happen. In quantum, this doesn't exactly work the same way. So at x not equal to x prime, your Laplace's equation holds, and you can solve the differential equation, which we're going to do next week, to be something like r to the L and r to the minus L plus 1. And then this is a Legendre polynomial, associate Legendre polynomial, cosine theta, and e to the plus or minus I m phi. Again, these are things we're going to be talking about over the next couple weeks. And so what happens is if we ignore the theta and phi components, we assume this perfect spherical symmetry, then is phi is supposed to go to 0. If r goes to infinity, that implies that you're going to have phi equal to a over r. In other words, L is equal to 0 is the common, the most basic solution if you're talking about spherical symmetry. And so what happens is you could say, well, 1 comes from the solution where if you integrate this thing, integrate the entire equation, then you get 1 from the delta function, and the integral of around a surface of delta d phi is equal to 4 pi r squared from integrating the surface area, and then taking the derivative of phi, you get minus a over r squared, which tells us that a has to be equal to 1 over 4 pi. And so, therefore, you could say that you have a Green's function for this thing, which is equal to minus 1 over 4 pi times r x minus x prime, the magnitude of that. So this is just a very, very quick and dirty way of justifying what is the Green's function that gives you your potential. And you'll notice that when you're trying to solve for the potential, and you look at any electrodynamics book, where a lot of the time this would not be a delta function. You actually have Poisson's equation, which looks like this. Then the solution for that is 1 over 4 pi epsilon naught integral of rho of x prime over x minus x prime. So this makes a lot of sense. What I would like to do on Thursday in recitation is I want to actually go through a more robust way of proving that this is true. And then that way you guys could see it. Okay. Also, before we get to that, I got another more robust way of showing you guys how to do this. And this is the example of a wave in 3D. All right, so what's happening here is we have the Laplacian of phi, which is going to be a function of both position and time here. This is equal to minus 1 over c squared times the derivative, our second derivative of phi, with respect to time. And we say that's equal to 0. Now, this is the standard wave equation you might see. What if we have an inhomogeneous form of this? So let's suppose we do the same thing, but I am going to put a I'm going to put a delta function on the right-hand side. Actually, two delta functions. So we have a delta function in space and one in time. And what this represents physically is, if you can imagine that you have your wave, but also you have a particle in the wave. And that particle exists at a specific place and time, and it's moving with the wave, or or somehow doing that. And you want to see, what does this particle see? So one way to solve this is to use our old friend, the Fourier transform, which you guys thought you were free of, where the Fourier transform is that you could take the inverse transform in the transform, and you could see that if we're doing k-space, this is the integral of phi of k and omega, where k is the wave number and omega is the angular frequency. And you have this term I, e to the I, k dot x minus omega t. And then phi is equal to the integral d cubed x integral dt of phi of x and t e to the minus I k dot x minus omega t. All right, so if you take the Fourier transform of this equation, what you're really going to be doing is, you could basically imagine you take this equation and you insert it into here. Okay? So we do the Fourier transform of the entire equation. So now what we have is basically the integral. And I'm going to do this explicitly just once, just so you guys can see, of actually no, let me back up. Okay. So what we're basically going to do is, we want to take the Fourier transform of the entire equation. So we're going to express this in terms of these variables. Okay? And so in doing that, when we take an integral and we take a like a Laplacian or something like that, the Laplacian is going to commute with the integral. So what's going to happen is we can actually take the phi here of this, and we're going to plug them into here, or here. And the delta functions here, well, by definition, a delta function of x minus x prime is equal to taking the integral over volume of e to the I k x minus x prime, like this. So what happens effectively is that we can actually substitute these for this stuff. And when we do that, we have a Laplacian is being applied to this entire equation, right? And when you take the Laplacian of this entire equation, the only thing in here it can take a derivative of, because this is the derivative with respect to x, is the exponential term. And so when you do that, you're going to get minus k squared times this guy. And then when you take this time derivative, it only really applies to the exponential term because that's the only time in there. So you're going to have plus 1 over c squared, actually this would be omega squared over c squared, times phi, okay, omega. And then over here on the other side, you're going to have, this is going to be replaced with this with this integral, and then the other one's going to be replaced with the other integral. And when we remove the integrals, we're just left with 1. So this entire differential equation is reduced to minus k squared plus omega over c squared, all multiplied by capital phi of k and omega is equal to 1. That is the solution to the differential equation. Does that make sense? Yeah. And again, this is one of those things you have to kind of be careful and convince yourself that you're right here, because what I actually did a lot of stuff at the same time. But I wrote it all with these, it would have been a lot to write out. But I wrote it all down essentially with the integrals, and then I just dropped the integrals because everything was inside the integrals. And so now, in order to find out what phi is, I could just do a simple division. So I get from that phi of k and omega is just simply equal to c squared divided by omega squared minus k squared c squared. And that's the solution. So now, what I do, now that I've solved my differential equation, I'm in k space and omega space. That's not right. I need time and space. So I have to get back to it. So I have phi of x and t should be equal to solving my integral. So I basically do an inverse transform on this. And then I have my solution, which is just c squared over omega squared minus k squared c squared. And then I have e to the I k dot x minus omega t. All right? And so I just have to solve this integral, and I'm done. And this is where, the stuff we learned about integrals comes in. Because first off, there's this volume integral I can solve. And so I already know that there's no phi term in here. The k dot x is going to give me a cosine theta term. So I can essentially, I'm going to skip some stuff, but essentially I'm going to have 1 over 2 pi cubed, and then I have c squared over IR, and that's going to come from R in this case is equal to the magnitude of x. And so that's going to come from taking this integral involving the dot product here. And remember, I'm integrating with respect to k. And so then I'm left with an integral from minus infinity to infinity of k dk. And then I have an integral from minus infinity to infinity of d omega. And then I have my exponential term, which now there's no dot product left. And then I have this term in the denominator. Okay? Now, to integrate this term right here with respect to omega, well, that's where we can use our complex variables, because you can see that there are poles in this. Omega equals IKC, right? And so there's poles at these terms, and so we can actually use that later on to solve this integral. So I can split my exponential between the k term and the omega term and solve both integrals like that. So what I'm going to do for now is I'm going to expand everything out, and then I can do that. So I have 1 over 2 pi cubed c over 2 1 over IR, integral from minus infinity to infinity of dk k, or sorry, dk e to the I k r and then I have the integral from minus infinity to infinity of d omega e to the I, or minus I omega t, and then I could split this term into omega minus k c minus 1 over omega plus kc. And that should be correct. And that's kind of where the k disappeared, is in the splitting here. So now what happens is I can use my Cauchy's Cauchy's integral theorem in order to calculate this, and I have my poles at ik, or at just kc, and so this ends up giving me 1 over c minus c over 8 pi squared r, integral from minus infinity to infinity dk e to the I kr, and then from this I'm going to end up with an e to the minus I k c t minus e to the plus I k c t. And what happens here is that between this exponential term, you can see you have an IKR and an IKT. This will end up giving me basically delta functions. So this is like C over 4 pi r times a delta function of r minus ct, and then another delta function r plus ct. And so what happens is, because r is positive and t is positive, this second one can't be true. So we must only have this solution. So what that means is that we have... Oh, which one? Right here? We had a factor of 2 come in because this went from minus infinity to infinity instead of 0 to infinity. So yeah, so we ended up having the factor of 2 pi I times that, which is where all that came in. So, yeah. So anyway, when we, we had a factor of 2 pi because of the, the delta function, the definition of delta function. And so we end up with a solution where our phi of x and r, or x and t, is equal to minus c over 4 pi r times the delta function of r minus ct. And so this is actually, they call this a retarded term because it basically says that you have to wait for your time to catch up for your position or something like that in order to actually see anything here. But essentially, the way that you interpret this is basically saying that you have a point and it moves with the wave. And so if the wave is moving with speed c, then you take the speed times the time and you get the location. And so I skipped a lot of stuff with this problem, and I do want you guys, did that just, for time's sake, but this is one of these problems where I think it's worth your time to actually go through and fill in all the steps. But the basic idea here is that you can solve this by, first off, even though it's an ugly equation, turn it into use the Fourier transforms in order to solve the differential equation. Know that the Green's function solution is the one that comes about when you have the delta functions on the right-hand side. And so once you solve the equation in the Fourier space, then you have to inverse transform it back. And that's the hard part, because then it means you got to solve this tough integral. But then what you're left with, effectively, is this, where this is the Green's function for this solution. And if we'd gone back and we put a function into the right-hand side, we could just integrate this with the function and we have our solution. So if we had, for example, the Laplacian of phi minus 1 over c squared partial phi partial t is equal to f of x and t, then our solution would have just been minus c over 4 pi r times the integral of over time and space of f of x and t with this delta function. And the delta function you could expand out as x minus x prime minus c times t minus t prime, all divided by the 1 over r. And so when you integrate this, the delta functions are fairly straightforward to resolve. And so you basically would resolve one of them, and you'd have 1 over 4 pi. Whoops, I didn't mean to put this r out in front, since we're integrating with respect to that. 1 over 4 pi times, you integrate it over time, then that resolves part of the delta function, and then you're just left with a spatial derivative of f of x prime, and then t minus 1 over c x minus x prime, all divided by x minus x prime. So in order to solve this, you'd actually need to completely solve it, you need to know what f is. And then this, like I said, this is a retarded solution. And it's retarded because the solution depends on the speed of the propagation of light or whatever the wave is moving at. If c goes to infinity, this term disappears and you just have f of x and t, and that's it.
The retardation also stated where the source is located.
Yeah. Well, the basic idea of the retarded potential is that you have a source, and you move that source, and you don't instantly know over here that the source moved. It takes a while. So moving the source doesn't instantly change the potential. It takes the time that the wave takes to travel before you can actually see that. It's interesting because we think of, in relativity, they talk about finite velocity of light and how that's one of the big things that makes relativity work, but it actually was in electrodynamics and Maxwell's equations where you first got that. And the whole idea that light doesn't just instantly travel, and that instantly moving something doesn't instantly change something. So for example, if the sun were to disappear right now, it would take us 8 minutes to notice. Not just because we freeze to death, but even the gravitational effects of the sun being gone would take 8 minutes to catch up with us. And there'd be no way to know before the 8 minutes is up. All right, so like I said, this is one of those problems where I really encourage you guys to just work it out in detail. And one thing I'm thinking I really want to do on Thursday is to just sort of work through the same thing, but just doing a simple Poisson equation, so you can see where that green function comes from for the for a point charge, or to actually solve that part of Maxwell's equation. So with that, I guess I'll see you guys on Thursday, and if you haven't already, please turn in your homework. And hopefully, like I said, this is like my absolute no guarantees week, but I might be able to get that by Thursday. If not, then we'll be able to talk about it next week.